In this demonstration, we explore how geospatial and climate data can be used to identify maize crop suitability. The objective here is to answer a key question: where can maize grow best under current conditions? And more importantly, how will this change in the near future? The final outputs of this demonstration will include a present maize crop suitability map as well as the future maize crop suitability map, which will show the zones of suitability. Our study area in this demonstration is the Corn Belt region of the United States, one of the most productive agricultural zones in the world. This region includes major agricultural states such as Iowa, Illinois, Indiana, Nebraska, and parts of Minnesota. The Corn Belt has highly fertile soils, favorable rainfall patterns, as well as moderate temperatures. These conditions make it one of the most productive maize growing zones globally. This makes it an ideal case study for climate-based crop suitability analysis. Let's continue by creating a new session and rename it based on our objective. To build this model, we use multiple datasets. Each dataset captures a different aspect for crop suitability. Let's upload them one by one. First, we are uploading bioclimatic variables from the WorldClim data. This dataset is called WorldClim version 2.1. It provides us 19 variables, including annual mean temperature, temperature seasonality, annual precipitation, as well as precipitation seasonality. These are global datasets available at multiple resolutions. They can be downloaded from the WorldClim website. Great, the present climatic variables have been uploaded. Next, we upload the future climatic projections. These future climatic projections come from global climate models, specifically MRI ESM 2.0 climate model under SSP 370 scenario. This represents a moderate to high emission scenario. It helps us simulate how climate conditions may evolve by 2050. This is a multi-band raster data consisting of 19 bands representing the corresponding variables. Great, the data has been uploaded as well. Next, we upload the crop distribution datasets. The first one is the GFSAD data. The full name is Global Food Security Analysis Data used for cropland extent. It is developed by NASA. It provides global cropland classification at high resolution. From this data, we can identify maize-related crop classes. Great, it has finished the upload process. The second crop data we are using is the SPAM data. Let's start the upload process. The SPAM 2020 Global Cropland Distribution Dataset is developed by IFPRI. This dataset provides crop-specific harvested area, spatial distribution of crops as well. It helps us identify the regions with high maize cultivation intensity. Great, all the input datasets have been uploaded. Let's finish off the upload process by uploading our study area boundary to focus our whole study on this region of interest. Great, the study area boundary has been uploaded along with other input parameters as well. All the datasets used in this demonstration are publicly available, globally consistent, and widely used in agricultural and research for climate. Once uploaded, they appear into the data catalog. From here, we can visualize before processing them. So let's start by visualizing some of the datasets. First, let's check out our study area boundary. Now, let's check the classified datasets for the crop data. Before jumping into the analysis, all the datasets uploaded into this session are standardized. So let's do the pre-processing step. In this first step, we align all rasters to a common coordinate system and resolution, ensuring that each pixel represents the same geographic location across all layers. Let's see what plan agent will show to execute the process. Here, the categorical rasters will be resampled carefully and the continuous data for the WorldClim rasters will be interpolated smoothly. Finally, everything will be clipped to the study area boundary. Great, the step 1 is completed. We can visualize these results to validate whether the process has completed correctly onto the map. Let's check out the GFSAD raster. As you can see, the dataset has been correctly aligned and clipped to the study area boundary. Next, we will generate some random sample points inside our study area. These points will be used as training dataset for training the model. These points will be evenly distributed to cover the entire study area. And later on, we will extract the input parameters onto these points. Great, the process has been completed and the sample points has been named as present points and saved in our data catalog. Let's visualize this layer on the map as well. As you can see, sample points have been created throughout the study area. Next, we need to identify the actual maize growing areas. For that, we will use the two independent crop datasets. So let's start one by one. From the GFSAD data, specific crop classes are converted into a binary maize layer. And similarly, the SPAM dataset is thresholded to identify the areas with high maize cultivation. This twofold procedure ensures that we capture reliable crop presence information from multiple sources. Great, this step is completed. Let's visualize the generated results. As you can see, the multi-class GFSAD data has been successfully converted to a binary raster with values of 1 and 0. And similar is the case for the SPM dataset. So let's move on. As we have successfully reclassified these crop data sets, it is important to attach this information to our training data. So we will extract these values to the points in the presence points dataset. Once these values from the two classified crop rasters will be extracted to the points, we will mark a point as maize presence only if both these datasets agree. That is, both the pixel values of these two rasters is 1 for a given point. This will improve reliability as well as this will remove the false positives. Great, the process is completed. All the raster values are extracted to the training points and a new field called maize present is created. Let's check out the attribute table to validate the results. As we can see, there are three new columns created. That is one for the GFSAD, second one for the SPAM, and third one to showcase the maize presence. Let's check out if there are actual records populated with maize presence is equal to 1. As you can see, there are the points selected which have maize presence. Now let's enrich each of the training points with the environmental variables which will be eventually be used for as a training data for the model. Here we are extracting the present 19 bioclimatic variables which represent temperature, precipitation and seasonal patterns. These variables are critical in determining where maize can grow successfully. Great, this process is completed. Great, all 19 variables have been extracted. Let's check out the attribute table to validate the process. Let's check out the attribute table to see if all values have been extracted. Before starting for the modeling part, we need to clean the existing datasets. Points with missing values are removed to ensure that the model is trained only on complete and reliable data. Great, the dataset has been cleaned and which can be used for training purposes. But before training the model, let's first generate the prediction grid on which the model can generate predictions. Creating this grid beforehand would make it convenient for us to directly feed this grid to the trained model for generating the predictions. For this grid, we create a fishnet of equal spacing on which we will again attach the input climate variables which will be eventually used for predictions and generation of suitability rasters. Great, the prediction points have been created. Now we attach both the present climatic variables as well as future climatic variables to the prediction grid. Great, the process is completed and both baseline and future bioclimatic variables have been extracted successfully to the prediction points. So let's check out the attribute table. Now let's get to the main part. We will now train the suitability model. Using the presence points and the baseline climatic variables, we are going to train this model. The model will learn the relationships between the climatic variables and the presence of maize. The agent has come up with a plan to train the model. Since maize points are relatively few, we apply techniques to balance the dataset, ensuring accurate learning. The result will be a model which will understand how environmental conditions influence the growth of maize. Great, the model has been trained successfully with the accuracy of close to 75% on the test dataset. Now let's generate the suitability map based upon the trained model. Each location gets a suitability score with values ranging from 0 to 1, with higher value indicating better conditions for the maize. Great, the baseline suitability raster has been generated. Let's check it out on the map. As you can see, this raster ranges from the values of 0 to 1, with higher value indicating greater suitability for growing maize. Now similarly, let's repeat the same process to generate the future climate data and future suitability raster. For this, we will be using the future bioclimatic variables instead of the baseline variables. Great, the future suitability raster has been generated as well. We can use both these future as well as present suitability rasters to identify the potential gain or loss over time in further analysis. And these rasters can also show how suitability for maize can change over time. Let's check out the suitability raster for the future. Generating these suitability maps for the present and future is the final step in this demonstration. Now let's move on to generate the report which will tell us about the modeling statistics and the accuracy metrics. Let's see the performance metrics the agent will print based upon our model. We have also asked the agent to print out the most important features used for training the model. These results will provide clear insights into the maize growing conditions. As you can see, the model has a considerable accuracy of close to 75%, and the top 10 predictors used in the model are: first one is Bio 9 and second one is Bio 17. We can also check out the maximum and minimum ranges for both the baseline and future suitability rasters. Value closer to 1 indicate higher model climate suitability for maize presence. Finally, we will ask the agent to produce the change detection map to see the gain or loss in the near future based upon the suitability standpoint. Great. The final results have been generated and the change detection analysis is completed. Let's check out the results onto the map. As you can see, the negative results indicate a projected decrease in the suitability, whereas the positive results indicate an increase in the future suitability. As per the agent, there is a mean change of slight overall decrease in suitability, but as we can see in the map, there are both increases and decreases present spatially. This brings our demonstration to an end. The final outputs of this study include a current baseline suitability map, a future suitability map, the model performance metrics, and finally the change detection analysis done on the both baseline and the future suitability data. This workflow highlights how climate and geospatial data can be transformed into a meaningful agriculture insights. We are not just identifying where maize grows today, we are understanding how suitability can shift under changing climatic conditions. Such insights are critical for crop planning, resource management, and long term resilience. At the same time, this entire analysis from data preparation to modeling and visualization is performed seamlessly within GriidAI. Without complex coding, we are able to process large data sets, build models, and generate actionable results. This is where geospatial intelligence meets real world decision making.